So, good morning. In the last lecture, I discussed about electromagnetic wave propagation in free space, non-conducting media, and the conducting media. And you saw that how differently the electromagnetic wave behave as they propagate in free space and the conducting media. In case of free space, the electromagnetic wave or electromagnetic field vectors move without any change in their magnitude throughout their propagation in the free space. And you also noticed that when they move in free space, the space offers a resistance of 377 ohm, and we call that resistance as the characteristic resistance. That is the resistance offered by the medium for the propagation of electromagnetic wave in free space. Then we discussed about the non-conducting medium, and in non-conducting medium we saw the only difference was that the velocity of the wave propagation was not equal to the velocity of light, but it is similar to the formula which we studied in optics. It is reduced by a factor n, that is refractive index, which is under root k. K is dielectric constant of the medium. But we did not discuss one thing in the last lecture. How does intrinsic impedance, the characteristic impedance offered by the conducting medium to an electromagnetic wave, changes in a conducting medium? So I'll do the same thing first before I switch over to the today's topic, and that is propagation of electromagnetic wave in an ionized media. We have made use of equation number 3 of the Maxwell's equation. Curl of E is minus del V over del T. But if you write B to be equal to mu H, so it becomes minus mu into del H over del T. If we break it into components, as we did in the case of free space, we can write this as del Ex over del Z. Z is the direction of propagation of the wave. It is minus mu into del Hy over del T. And now we are going to substitute the value of Ex and Hy that we calculated in the last lecture. You saw that the value of K, the propagation constant in case of conducting media, was equal to beta plus J alpha. Beta plus J alpha was the value of alpha plus J beta was the value of the propagation constant. It has an imaginary component as well. So we will make use of the same expression for E. We wrote E was equal to E0, e to the power of minus beta Z, and then e to the power of J omega T minus alpha Z. Alpha is the phase constant, beta is the attenuation constant. So if you substitute those values here, then it comes out to be minus beta minus J alpha into Ex is now equal to minus J omega mu into Hy. Let us take now the ratio of the electric field and the magnetic field vector. So the ratio of the two comes out to be minus J omega mu upon beta plus J alpha. We substitute the value of alpha and beta now. Alpha and beta are under root omega mu sigma upon root 2. So we put them here and we can rewrite it as J upon 1 plus J under root of 2 omega mu upon sigma. And to just remove this complex function from the denominator, we multiply it by complex conjugate and divide it by the same factor 1 minus J. So 1 plus J into 1 minus J basically becomes 2. So we have 2 here, but we have under root 2 in the denominator, in the numerator, so it becomes root 2. Similarly, J into 1 is J and J into minus J is plus 1. So that is why it becomes 1 plus J upon root 2 into under root of omega mu upon sigma. So if you recall the definition of intrinsic impedance of a medium here, the intrinsic impedance of a medium here is basically a vector quantity, or an imaginary component is also there. So imaginary, if you take the mod 1 plus j by root 2 mod will be equal to 1, and the intrinsic impedance will be equal to under root of omega mu upon sigma. You can see yourself that it depends upon the conductivity of a medium. Larger the conductivity, lesser will be the intrinsic impedance offered by the medium for the propagation of electromagnetic wave in the medium. Then you have a factor 1 plus ij. If we write this as r cos theta and r sin theta, that means r e to the power of I theta, we will have a phase angle of 45 degree in between, because sine component, cosine components are same, the 1 by root 2, 1 by root 2. So this will give rise to the factor of the angle of 45 degree. So 45 degree means the electric field vector and the magnetic field vector, they are not in phase. In fact, electric field leads by an angle of pi by 4 radian in good conductor. So we have to just understand the difference between the propagation of electromagnetic wave in the conducting media and the non-conducting media. In non-conducting media, the resistance offered by the medium is 377 ohm. Here it is less, and it depends upon omega, mu and sigma. And there is a phase lag, there is a phase difference of pi by 4 between the two electric field vector in a good conductor. After this, let us now discuss about propagation of electromagnetic waves in ionized gases. So propagation of electromagnetic waves in ionized gases, the difference between the conducting media and the ionized gases is just like this. In case of conducting media, the conduction takes place because of the conduction electrons, while in case of ionized media, the conduction will be because of the movement of ions and the electrons. Ionized gas is nothing but the plasma. We will discuss these things in more detail while discussing plasma. So plasma is nothing but ionized gas. So you simply understand that you are given a gas, you ionize it by any means. You can have a discharge. So when you discharge the electron, the ions are, the gas is ionized. So ionized gas, we will have the ions and the electrons. So if you put them in the electric field or you apply the electric field, both the electrons and ions will move. So in this case also, the conductivity will not be equal to 0. We can consider the volume charge density to be equal to 0. The value of mu is mu 0 and epsilon is epsilon 0. So we write again the equations for the Maxwell equation in the same way as we wrote for a conducting media. We will do the same thing here again. We will take the curl of equation number 3 and we get the similar equation that we got for the conducting media. Del square E is mu naught epsilon naught del square E over del T square plus mu naught sigma del E over del T. Similarly, del square H can be obtained by taking the curl of equation number 4 and we get back the similar equation, only E is replaced by H. The beauty of doing all these things is that we can solve both the equations on the similar footing because you don't have a difference except E is replaced by H. So both the equations can be solved by the same method. So let us write down the general solution as it is again a perturbed equation. We have a perturbed term mu 0 sigma del E over del T. So we will write down the solution as E is equal to E0, e to the power of j omega t minus kz, and similarly the magnetic field component H will be equal to H0 e to the power of j into omega t minus kz. But here we will analyze the things in a slightly different way. Let us now put back the value of E in our wave equations or in our equations, equation number 5. If you substitute them, we get an equation K square is mu naught epsilon naught into omega square minus j mu naught sigma omega, which is same as the equation that we got for the conducting media. And after equation 6, what we assumed there that since sigma is larger, so we neglected the real term. I wrote K square to be equal to minus j into mu naught into sigma into mu. But here we are not going to throw this term away. Now we will write down the current density by applying the Ohm's law. Ohm's law says that J is equal to sigma E. the current density in a medium or in an ionized gas can be written as sigma. Sigma is its conductivity and E is the applied electric field. So when we apply the electric field E to be equal to E0 e to the power of j omega t minus kz, so there will be a force acting on the electron, and we can make use of the simple Newton's second law of motion to find out its velocity, because you can recall the expression for j as j is equal to n into E into B. N is the electron density, E is the electron charge, and B is the velocity of the electron. So if we really want to compare the two terms, J is equal to sigma E and J is equal to N into E into B, we must have the idea of the velocity of the electron when we put the entire system into the electric field. So the force experienced by the electron here will be equal to F is equal to E into E, because that is the force experienced by the electron in electric field E, and the electric field E is E0 e to the power of j into omega t minus kz. So now F is equal to m into A according to the Newton's second law, but here I have written it as m into dv over dt. dv over dt is nothing but the acceleration. So dv over dt is now E0 upon m e to the power of j into omega t minus kz. Here B, if you integrate this equation, so dB over dt is now this one. If you integrate, the value of a B will now be equal to E0 upon j omega m e to the power of j omega t minus kz, plus a constant of integration will also come into picture, but I have not written that constant of integration. The reason is, when the electric field was equal to 0, all the electrons basically wander here and there. So due to the random motion of all the electrons together, if you consider a system as a whole, the net average velocity, the net average initial velocity is basically 0. So if you put basically is at t is equal to 0, if electric field is equal to 0, the velocity is 0. So the constant of integration will be equal to 0, and we can write down the velocity B as E0 upon j omega m into e to the power j omega t minus kz. Now we put this value in the current density expression, j is equal to n into B. So this becomes now sigma into E0 e to the power of j omega t minus kz, and now we compare the two expressions, j is equal to sigma E and j is equal to n into E into B. So you can see equation number 7 and equation number 8. If you put them together, the electric field term drops out from both sides, and we are left with the expression for sigma, that is the conductivity, and sigma comes out to be minus j n e square upon m omega. Equation number 6, we got a relation k square is equal to omega square into mu naught epsilon naught. Mu naught into epsilon naught is 1 over c square. So k square is omega square over c square minus j into mu naught into sigma into omega. We multiply both sides by c square. So we have k square c square is equal to omega square minus j into mu naught c square sigma into omega. And now we substitute the value of sigma that we calculated by comparing j is equal to sigma e and j is equal to n into e into b. So if you make a substitution for this value here, then we are left with a very simple equation, that is omega square minus n e square upon m into epsilon 0. In today's lecture, you can consider this n e square upon m into epsilon 0 as a term which is a square of frequency from the dimensional point of view. This frequency, when we will discuss about plasma, this is the plasma frequency. Omega p is the plasma frequency, and omega p can be written as under root of n e square divided by m into epsilon 0. Plasma frequency depends upon the number density of electrons. Larger the density of electron, more will be the plasma frequency. The relation between the plasma frequency and omega p, omega is 2 pi times frequency. So frequency can be written as Fp is equal to 1 upon 2 pi under root of n e square upon m omega e square. Now the value of E is known to you. It is 1.6 into 10 to the power minus 19. The mass of the electron is known to you, 9.1 into 10 to the power minus 31. Epsilon 0 is 8.85 into 10 to the power of minus 12. So you substitute all these values and make the calculations. You will find that all these terms comes out to be 9. So it's a 9 under root of n. If you remember, if you work out this formula once, you can remember it. And by using this formula, you can directly calculate the frequency of plasma oscillations by knowing the plasma density, the plasma electron density. Plasma electron density here is n, and we can write this as 9 into under root of n. And this equation, omega square minus omega p square is equal to k square c square. This relation is called dispersion relation. So we will now understand two cases. The one is when omega is larger than p, when the frequency of electromagnetic wave propagating the ionized medium is larger than omega p. Omega p is the plasma frequency. Omega square minus omega p square will be a positive quantity. So k square is positive. So k is real, and therefore the free propagation of a wave into the medium is possible. But if you consider the other case, that if omega is less than omega p, that means if the frequency is less than the plasma frequency, the value of k is now imaginary. So therefore that leads to the attenuation. So this relation helps us to find out which waves will propagate through the ionized medium and which wave will not, and it all depends upon the plasma frequency. That means all the waves having the frequency larger than the plasma frequency will be allowed by the plasma to pass through, while the frequency having the frequency less than the plasma frequency will be attenuated, or their effect is limited to few skin depth only. Let us now write down the refractive index of a medium also. Refractive index n is equal to c by b, that you already know, and the velocity b is given by omega over k. So this becomes now ck upon omega. Ck, from this equation, k square c square is omega square minus omega p square. So ck now becomes equal to under root of omega square minus omega p square. So we take omega inside, so it again becomes 1 minus omega p square upon omega square. Again, you can check both the cases. If omega is larger than omega p, so if omega is larger than omega p, then in that case, this term will be less than 1. The value of refractive index will be real, and the propagation of the wave into the medium, into the ionized medium, will be possible. While if omega is less than omega p, you can see yourself that the term along with 1 will be larger than 1. And in that case, it is imaginary. The omega is less than omega p. It's imaginary. So its effect is limited to basically few skin depth only. I'm not calculating basically skin depth again, but otherwise, when we will talk about plasma, that is the other 50% of your course. In plasma, we will discuss about ionosphere also. In the last lecture also, I gave you the idea of ionosphere, but in ionosphere is nothing but the ionized gas. So it comes with this dispersion relation is very useful in ionosphere. And the study of ionosphere is very important to understand basically the propagation and basically the communication also. So here, in case of, in fact, if you, as I told you in the last lecture, if you start moving from the Earth's surface and go up and up, at a certain place, you will come across the ionosphere. If you go deeper and deeper the ionosphere, the density of electron will keep on increasing. So what will happen if you allow a radio wave to propagate towards the ionosphere? It will penetrate, and the moment the condition omega less than omega p will come, the wave will come back. And that is how basically the ionosphere is being used for transmission from communication purpose. Communication, there are several ways of communication. Nowadays, we are relying basically on optical fiber communication, but this was also a medium of communication. Even it is also tried today also. So you have to understand how the communication through ionosphere is possible by understanding the solution of all Maxwell equation in a ionized gas. So we will discuss more about these things, more about the ionized medium when we will talk about plasma, because all these things are applicable to the plasma as well. Plasma is nothing but the ionized gas or a system containing the charged particle, charged ions or positively charged ions, negatively charged electrons, and the neutral. In fact, we call this system as a whole as plasma. Now we come back to the electrodynamics. So before I switch over further, there are certain formula in vector calculus that you all have to remember. And even if you don't remember, you will have to appreciate all those formula. So if you know about the formula, then only you will be able to appreciate. The first formula is curl of a gradient of a scalar quantity is always equal to 0. I will suggest you all to basically expand it. Write gradient of S as del V over I cap into del V over del X plus J cap del V over del Y plus K cap del V over del Z. And now you expand this curl of gradient of S. So curl of gradient of S, you write down IJK in the second row of the determinant, del over del X, del over del Y, del over del Z, and then you write del S over del X, del S over del Y, and del over del Z, and check yourself that this gives us 0. So curl of the gradient of a scalar quantity, remember, yes, it is scalar. That is why I have not put a bar over here, because we have a gradient. So gradient makes it vector. So curl of a gradient of a scalar quantity is always equal to 0. And another identity in vector calculus is divergence of a curl of a vector quantity is also equal to 0. So here you have to write down V. V is vector right now. So V is I cap into Vx plus J cap into Vy plus K cap into Vz. And you all have to verify that divergence of the curl of a vector quantity is equal to 0, as we will be using these two formula quite often. The third formula that you must have read is A cross B cross C formula. In fact, A cross B cross C is B into A dot C minus C into A dot B. So you can remember this formula A cross B cross C as BAC minus CAB formula. So you remember the sequence, and once you remember the sequence, so it is BAC minus CAB. And I hope once you write it 1-2 times, 2-3 times, then you will be able to write it fully. The next formula is a del cross A. I have used basically this formula several times in the last 2 or 3 lectures. So it is del cross A is a del gradient of divergence of A minus del square A. This formula is also very important. The next formula that we will be using in the coming lectures is del cross A cross B. Del cross A cross B is B dot del into A minus A dot del into B plus A into gradient of B minus B into gradient of A. This is one formula. And the other formula is gradient of A dot B is A cross B plus B cross A plus A dot del into B plus B dot del into A. If you look at the formula number 6, so here in formula number 6, suppose we take A and B are same. If it is A and B are same, or they are both equal to A, so the left hand side becomes A dot A. So A dot A becomes A square. So gradient of A square or gradient of A dot A is the first term A cross A and A cross A becomes the same. Similarly, the third term and the fourth term A dot del into A and B dot del into A also becomes the same. And therefore, if A and B are the same, we can write down this formula as gradient of A dot A to be equal to twice of A cross A plus A dot del into A. Or we can take this 2 on this side and then we can make use of this formula. So you will see this, the formula number 6 is also useful when we will discuss about the Ionized potential. The formula number 6 is very useful. The other thing that you have to remember is divergence of A cross B is B dot curl of A minus A dot gradient of B. These are basically some of the formula of vector calculus that we will be using, and you all have to have them in your copy so that you can check because it's sometimes difficult to remember. So we have to basically copy this formula while moving further. Then now you are familiar with the three types of three type of coordinate system: the Cartesian coordinate system, the spherical polar coordinate system, and the cylindrical polar coordinate system. In Cartesian coordinate system, in fact, in the three-dimensional coordinate system, you can consider a plane having x and y axis. You can consider the corner of your room and let the two sides of your room are x and y axis, and the third axis, which is one of the wall or the joint of the two walls, you can consider as the z axis. If you consider a point lying in your room, you drop a perpendicular on the z-axis, and the distance of the foot of perpendicular on the z-axis from the origin of the coordinate system will be the z-coordinate of the particle. Now you drop a perpendicular from the same point onto x and y plane. So on the xy plane, it is going to meet somewhere. Drop a perpendicular from the foot of perpendicular on the xy plane on the x and y axis, and measure the distance of the perpendicular, the foot of perpendicular on the x and y axis. So that will give you the x and y coordinate, and that is why how we define x, y, and z coordinate in the Cartesian coordinate system. Then now coming to the spherical polar coordinate system, you can see the diagram here. In spherical polar coordinates, x, y, and the z axis you can see. Suppose I take a point somewhere here, you can see the figure. This point, I join this point to the origin of the coordinate system. So this is our radial axis. So radial axis, the angle made by this radial vector with the z axis is basically the theta coordinate. Now you drop a perpendicular from this point onto the xy plane. It is going to meet somewhere on the xy plane. You join the origin of the coordinate system to the foot of perpendicular on the xy plane. The angle made by that line with the x-axis will be our angle phi. And if you make use of this formula, you can easily write x to be equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. So these are basically the coordinates. R is called radial coordinates here. Theta is called polar angle, and phi is called azimuthal angle. In some places in future, we will say that the system has azimuthal symmetry. Azimuthal symmetry means the physical parameter does not depend upon the azimuthal angle, that is phi here. So you have to remember, I have not written the expression for the length element, the surface element, the volume element, the gradient, the divergence, and the curl for spherical polar coordinates. But at certain places, we have to make use of those coordinates also, those parameters also, those formula also, to basically understand or to proceed further. So I will suggest all of you to write down all those formula for gradient, divergence, curl, line element, surface element, and volume element for both the spherical polar coordinates as well as the cylindrical polar coordinates. Now coming to the cylindrical polar coordinates, here we had r theta phi. In cylindrical polar coordinates, we have r, theta, and z. R theta and Z. So here R is similar to the spherical polar coordinates. Phi is similar to the spherical polar coordinates, but Z coordinate is similar to the Cartesian coordinates. So that is how it will be easier for you to understand. So here the relation are x is equal to r cos phi, y is equal to r sin phi, and z is equal to z. You can see the figure. Here I have taken the same two axes that I took for defining the spherical polar coordinates, x and y. Here there is a vector r, there is a point P. If you join it with the z axis, so it points along the radial direction. The vector pointing along the z direction is basically the z coordinate, and the unit vector along it is z cap. So z cap, r cap and phi cap are nothing but the unit vector representing the three axes of cylindrical polar coordinate system. In some books you will find they write I r, I theta and I phi, but most of the time I will be using r cap, phi cap and z cap as unit vector in cylindrical polar coordinates, and coming to the spherical polar coordinates I will use r cap, theta cap and phi cap. So here again r x is equal to r cos phi, y is equal to r sin phi. You can obtain these components very easily from the figure that is shown here. And then the value of z is simply z. And again, I will suggest you to write down the expression for the line element, surface element and the volume element along with the gradient, divergence and the curl. And if the need be, then what are the limits of integration that we have to make use of while exploiting these coordinates. So in cylindrical polar coordinates, the value of r or the range for r is 0 to infinity. The value of phi is 0 to pi, and the value of a z is minus infinity to plus infinity. So all these things you have to revise. In fact, you have to revise these are gradient, divergence, curl. I will suggest it because you have plenty of time these days. So I will suggest each one of you to basically read about gradient, divergence and curl from the physics point of view. Because what idea you have right now, that if somebody asks you what is gradient, what is divergence, what is curl, you understand them as basically a mathematical tool to solve basically the vector calculus problem. But if you read, I will suggest each one of you to read the book by Griffith. And if you read Griffith, you will understand the underlying physics associated with the gradient, divergence, and the curl. And you will enjoy how useful these parameters are, how physically significant these parameters are to understand basically the physics problem. So this was basically the introduction. In the next lecture, I will discuss about now the scalar and vector potential, and that is basically the beginning of your course, and those things will be new because you must have read these things earlier also as far as the Maxwell equations are concerned. So we will discuss about scalar and vector potential and then more about these electromagnetic waves from next lecture onwards. Thank you very much.